Right? Yeah. Okay, here we go. Okay, Gustavo said start slowly. I will start slowly. People are still like, I want a Higgs factory now, and everybody is totally like focused, and the future is coming at us. Okay. So the door is uninvitingly closed, so let's... So, more classification today. So, just to remind ourselves, like where we stopped yesterday, we talked about classification, and like, my standard like example for classification I told you is top tagging. So you analyze jets, and you try to like tell apart QCD jets from top jets. Why? Because it's simple, it's easy, it's well defined, no extra trouble, right? I mean, you want to show that methods work, right? And if you want to show that methods work, don't make it like, unreasonably hard in the beginning, because they might, not be convincing. The results might not be convincing. And you can always add difficulties later, and we will. And at some point, when things get really hard, as Pheno people, right, we hand it over to our experimental friends and said, like, oh, here you go. And, deal with it. It's a really good idea I had. It just needs a little bit fixing left and right. Sorry, like I'm on camera, right? Okay, so thank you, experimentalists, for doing that for us. What I showed you last time is if you want a classic network already, like if you can use the word classic in machine learning, pointing to something that was discovered like 10 or 15 years at most in the past. But like a classic network is a convolution network. And the convolution network is, I guess, to some level, what made modern image analysis possible. And the convolution network, I told you in particle physics, well, it's very simple. You look at this jet image, whereas chalk, you look at this jet image, and the jet image is really like, if you think about like, it's a slice of colorimeter. And there's a slice of colorimeter, like, let's assume it's square, whatever, like eta and phi. And if you rely on the colorimeter, it's pixel. And a jet image then has, like, well, think 40 by 40, at most 100 by 100 pixels or something like that, and they're colored in. And, like, a bunch of, like, objects, like subjet objects, constituents of the jet hit that image if you want, and, like, color in these pixels. And you're talking about, like, 20, 30 of those, like, 1,000 or 2,000, a few thousand pixels being colored in, at most 100. So, like, this is a very sparse image. And I told you, like, what they look like is, if you're lucky, then a top jet looks like that. Like, clusters, 3 of them, with a little bit of stuff here and here and here. And then I showed you that, like, when you use these convolution networks, what you do is, for instance, you're defining yourself a 3 by 3 filter, and you run over that pixelated image, and you're trying to learn a filter. And the important thing for the, in using these convolution networks is that these filters are learned not as a function of the point where, like, their center is, but globally. So you learn the filter. You don't learn the filter and the function locally, right? I mean, you learn a global filter pattern. One thing I didn't talk about last time is you can improve the situation by running filters of different size. Why would that be? Because, you could have, for instance, like, some kind of a correlation which, like, is preferably, like, top left to bottom right, but you don't know at, like, which resolution that is, right? So here then you would run the filter and, like, to change the size of the filter, and then you could accommodate that. So this is all fine, all done. Now if you think about it, these filters, you look at these images, and you think about it, and the more you think about it, the less you're convinced that that should work. Because we have an image that, like, is super, super sparse. And we're running a filter over it, like, that discovers, if you think about it, mostly nothing. Like, wherever this filter is, it sees mostly nothing, right? And at some point, it might see, like, a little bit of a pattern, but it sees mostly nothing. So like, you know, it's not, it doesn't strike me as a particularly good idea to use a convolution network over a very sparse image. Now, luckily, the whole thing works. So otherwise, like, I wouldn't be here, like, you know, like, because everybody doing this kind of research has started with these kind of convolution networks. But if you think about them, convolution network is not what we want to use for these sparse images. It's just the first thing you try, and if the first thing you try works, well, you publish a nice paper and get famous or something like Ben Nachman did, right? But you step back and said, no. Hello. So you step back and said, like, you know, that shouldn't work. And also, like, you know, there's probably better ideas of representing this data. And I'll talk a little bit about like 2 other approaches now. Be a little bit like, you know, less detailed because, you know, they're more complicated. Before I do that, like, you know, in my lecture notes, I'm skipping a lot of chapters. I'm skipping the chapter where I could have shown you how you can do that with error bars. Bayesian networks, same thing, right? I mean, there's no reason to not use this, like, you know, uncertainty, like aware networks for classification. You can do that. Just the same as for the regression tasks. And then also, I mean, you see, these jet images, what they do is, like, you know, then they learn these filters or feature maps, and then like they learn, like, you know, several like of them, like you stack these feature maps and you analyze them all in parallel. Because essentially, you don't trust one of them. Like, you know, so that, like, you know, adds to the resilience of the network. Like, you're learning always a stack of filters. And there's a super cool network architecture that makes use of those, like, you know, stacks by combining them. Like, essentially, you know, when you like drill through ice at the South Pole to research, right? You drill, like, you know, these things into the ice. Like, you know, think about, like, you know, a network architecture where you drill through these, like, through these feature maps, and you're correlating them, and you're like, your network output is not a scalar value here, but it's a vector that goes through the feature map space, right? And then, like, you know, you're allowing the network to correlate all of this and to organize this information. It's a beautiful network. It's called Capsule Networks. It's a natural, like, extension of these, like, CNNs. I love them. The problem is, I don't know, it's one of these dead ends, like, you know, because what I'm going to show you next just works better. So, like, you know, these capsule networks are great. Think about them. At some point, read the stuff. And while I'm going to go and talk about a more appropriate representation. Because the representation that we really, like, you know, have here is not that, right? The representation that, like, a theorist sees is a bunch of objects, I, and all of them have an energy and momentum. And, like, you know, you can organize them, if you want, in a matrix or something like that. So you have, like, you know, an energy entry, and you have K1, K2, K3 for, like, you know, the three momenta here of all part objects that you're looking at. For the first particle you look at, and for the second particle you look at, and for the third particle you look at, etc. So that's really our data. I mean, this is what the good. If you look at, like, you know, what we call particle flow output, I mean, this is what the experimentalists give you, or, like, you know, what the experimentalists read out is a bunch of energy and momentum measurements. We can represent it that way, but we can also say, look, what we have here is a bunch of four momenta, and they live in a space. I mean, we know what space that might be, like, you know, how you combine them. Still, if you don't know, I mean, if you have a bunch of data representations that live in a high-dimensional space, you don't know what that space is, that thing is actually called a point cloud. A point cloud is essentially data representation, like, you know, for instance, in vectors or something, where you, per se, you don't know what the space is. Like, you know, there's always some space behind it, like, you know, always some kind of metric, but, like, you know, point cloud is essentially the case where I don't know what it is. Maybe my network will learn it. And when you analyze, like, you know, this kind of point cloud data, like, you put this into a network. I'm not going to talk about the details of that network. Like, you know, we've played with this. You know what the result should be in terms of, like, you know, how do I combine different four vectors, like, you know, to somehow make a statement about, like, you know, properties of a jet, right? You have two different, I mean, the statement top versus QCD, right, is to first approximation a Lorentz scalar, right? I mean, like, it's like, it shouldn't depend on these kind of, like, on Lorentz transformations. So essentially, you know that whatever you put into that decision should be approximately Lorentz scalars. Like, for instance, invariant masses. And we know the jet mass, for instance, is one of the key measurements that decides if you have a QCD jet or you have a top jet. So for this point cloud here, in some appropriate representation, I know what the metric is. You know, the metric that actually allows me to combine these kind of 4 vectors and make a statement about quarks and gluons versus tops has roughly the form here, like this. It's a diagonal matrix, and it's roughly, like we measured that, 0.99 plus minus 0.02, and then it's minus 1.01 plus minus 0.01. And then the next entry would be the same, minus 1.01 plus minus 0.02. And then the last one is minus 0.99 plus minus 0.02. This is the underlying metric. You might have heard of it. That's the underlying metric that allows us to combine these point cloud 4 vectors to make a statement about quark or gluon versus top jets. Right? Just write it up. It's important because like, this is possibly the only time that like somebody will write the Minkowski metric on the blackboard with error bars. Which is exactly what's happening. Now, by the way, and this sounds trivial, I mean, of course, like, if you look, derive something from invariant masses, you know that has to be the Minkowski metric. This actually, I'm making this more trivial than it is, because you think about it, if you have lots of information, for instance, just in the spatial correlations of these 4 vectors, then of course it's not the Minkowski metric. So you could try to derive stuff from 3 vectors ignoring the energy entries, and then the metric is going to be something different, right? But still, so like, this is like, I think groundbreaking. So what we now have is, we have a point cloud, and we have an idea about the metric, the underlying space that point cloud lives in. I'm recorded, right? Let's think about cutting this. Okay, so I was, by the way, my senior colleagues, I was strongly advised not to put that into the paper. Because I said, you're not going to get that published. And we did. So now, if I think about these like, point cloud representations, like just write this down more general. Imagine you have like, some space. And think about like more like 2-dimension space, so like I can visualize it. So then I can write like, my representation here also like this. Like, here's like an object, here's an object, here's an object, here's an object, here's an object. And there's more of them, right? I mean, these are like, objects, I just like number them. 1, 2, 3, 4, 5, for instance, right? These are now my little like pixels, which are, think of them as my pixels which are like colored in. But I'm dropping everything that's empty. So that's a much more minimalist representation, right? And now I have those pixels which are like colored in. And the next question I want to know is, okay, like how far are they apart? Remember that our like C and N always runs a filter over neighboring objects. So now I want to know how far are they? Like, how far? Like, how do I get from one to the other? So you could, for instance, say, okay, let me write down like neighbors links, and like on a second, like 1 is close to 2, and 1 is close to 3, 1 is close to 5, and 2 and 5 are also close to each other, but like 2 and 3 are close to each other, 2 and 4 are not neighbors, but these are neighbors and those are neighbors. Right? Now I'm basically defining myself a neighborhood, following this one here. So now these kind of objects are called graphs. Graphs are essentially point clouds where you have an idea like, of proximity in whatever this underlying space is. Right? This underlying space I can make an assumption about, but I can also try to train a network to learn it. The key object that you want to look at when you look at these graphs is the so-called adjacency matrix. So what you have here is, you have, just for the naming, you have nodes here. Our objects, our 4 vectors will be called nodes. And like the links between the two of them would be called edges typically in machine learning language. And now you can describe like, your neighborhood definition using a matrix A. And that's a 5x5 matrix. And it's very simple. You put like aside from, of the diagonal, you're putting ones if these things are neighbors and zeros if they're not. Yes?
Again, how do you define the nodes? Just any pixel that's not...
Yeah, these are just the pixels. Or these 4-vector entries. Right, you can also think of like, these are the pixels or they're the 4 vectors, like, wherever they hit.
No, like the pixel you can still adjacency is literally in the pixel space, but if it's the 4-vector, well, how do you...
Right. Yeah. Oh. Yeah. I know, it's like there is a secret metric. But like, aside from that, you don't know. You're completely right. How do I find adjacency matrix? But like, if I have one, like somebody gives me an adjacency matrix, I can write it down. And the structure is very simple. So here, for instance, like, 1 and 2 here have a 1. And then like, 2 and 3 have a 1. The question here is, does 1 have a link to itself? Let's just assume like, you can link this to yourself. This is like a little bit of a mathematical detail, but you have 2 choices. Either you have a closed path or you have no closed path, in which case that would be counted as 2 and this would be counted as 1. And so on and so forth. So it's just a bunch of, and it's obviously at this stage symmetric. So like, you can just like, right, 2 to 1 here, 1. So like, you can do these adjacency matrices. 1, 1, 1. You can check if that's true. It's going to get more complicated in a second when I can just discuss some more about this matrix. So this adjacency matrix basically tells you where the neighbors are. You're laughing. Where did I screw them? 1, 1, 1, 1, 1, 1, 1, 1. This is a 0. It's at least symmetric. No, it's not. It's almost symmetric. Like that's also a certain error bar. Okay, so this is the adjacency matrix. And this adjacency matrix tells me if I sit at 1, like, here, what are my neighbors? And like, it tells me my neighbor here at 1 is like, I have a self-connection to 1. My neighbors to 1 are 2 and 5, for instance. And that's very useful. Just as a side remark, this adjacency matrix is even cooler because if you, for instance, square it, we don't need that feature, but I think it's kind of nice. If you square it, it has like, a structure that looks like 6 to 3 and so on and so forth, right? What this adjacency matrix squared tells you is the number of paths I have that go from, say, like 1 to 1 or 1 to 2 or 2 to 2 at length the power. So that tells me that, like, if I want to go from, like, 1 to 2, I can go from here over to 1 and here, 1 path. This here has a direction, so I can go so the other way around and go to here is 2, and I can go through here, 3. So it's exactly that, right? So if you go from 2 to 2, you can go 1, you go here and back, here and back, here and back. There's a 3. Right? If you go from 1 to 1, you have 1 here, and then you have these things the other way around. So like, so essentially what you can do is you can take a power of the adjacency matrix, and it tells you something about how close and how many possibilities you have to go from A to B at a given length. As I said, this is not a feature that we ever use. We use this thing much more basically. So let's erase that. So what we do instead here is we now take our graph network, our convolution network that we've had before, and remember that had like an xi. It had an index ij originally, but now I'm just running through these nodes, so I'm removing one of those 2 indices, right? And I link these things. Remember, I had a sum of all kinds of neighbors. Neighbors, and then I had an ij, xj. And I'm forgetting the bias term now because it's like, a pain in the ass to write down. Yeah? So this is, if you want, our old network here, if I write this in 1-dimensional, just by attaching numbers to every pixel. Right? So this is and then I'm writing here Well, this is a sum over all the neighbors j. It's not mathematically as nice as the real formula we had, but this tells you what it's all about, because if you now think about it, this adjacency matrix comes in super handy, because now what I can do is I can actually replace this by a sum over all j's, wij, and then I have, or j prime, I have the adjacency matrix j prime j xj. Because the adjacency matrix is like, forget about the diagonal terms, the self-correlations. Aside from that, the adjacency matrix basically is 0 if it's not a neighbor, and it's 1 if it's a neighbor, right? Okay, I can write that. In this form, though, I can run it over my graph. Because my graph is defined by the adjacency matrix. So what I can do now is I can take the standard, like a convolution network, and I can run it over my nodes, where I have edges, and the existence of edges is encoded in the adjacency matrix. And what I do now is I take my graph network, my graph representation, and I run my filter over the different nodes in the graph, always computing the filter as a function of all the neighbors, and you want next to neighbors, whatever you want to do there, right? So what you can do then here is you can run this, use this formula to run the convolution network on graphs. But it's much more economic, because I told you that here we have 40 by 40, so we have 1,600 of these things, but when you run a graph network on that, you run over 20 or 30 of these constituents. The other thing is, if your image here is not just the energy, but it has a whole vector of properties, and add the charge if you want, right? You can run this thing you can make a vector out of that, right? No problem. It goes like that. Right? And you can evaluate this thing now completely in an abstract space by essentially doing a convolution network over graphs, over the graph nodes, and neighborhoods are defined by edges. Which brings us to the question, what are my neighbors?
Why is it computationally better? Because the matrices are still n by n, right? The W and the A are still n by n.
No. This is, you're running over far fewer points here. Right, numerically, here you have to evaluate your filter at every single point. At every single point, you essentially calculate, or almost all of these points, you calculate as 0. Right? Here, you're essentially only picking those filter positions where something is happening in your filter ideal in the center node. So walking through an image, think about it, if you have you're walking your network through an image, here you have to essentially walk over every pixel and evaluate some kind of filter.
No, I understand the logic, just mathematically. The W upstairs and W downstairs are the same size of matrix.
Yes and no. See, the W here factorizes into this W in the adjacency matrix, and I'm only taking the diagonal and off diagonal, first off diagonal here. Everything else is 0. But that's the next question. But let me answer the first question that you had, which I forgot. What was it? Oh, the neighbors. How do I define the neighbors? Well, that is actually a good question, because I don't know. I'll start with this one, and then you see what you can do. It's a little harder, right? When you think about what's my metric to combine the entry charge, plus 1, minus 1. I mean, is this an attractive thing? Is this a repulsive thing? I don't know. Right? I mean, so the network. And the question if this is attractive and repulsive depends on the task of your network. You don't know, there is no God-given structure of E plus and E plus E minus, neighborhood in in an event to search for squawk pairs. I don't know what the answer is. So let my network learn that. Just one thing I want to write down, So in general, here we're writing the sum over neighbors. W's times x. If you think about it, there's no reason to just sum here. I mean, there's a million ways of combining these kind of things. For instance, means, minimum, maximum, anything you can do, right? So you can further generalize this by basically defining an xi prime as something acting on all combinations j with this original x, some kind of operation that depends on the network xi, and that knows xi and xj. And that thing here is called an aggregation function. And that aggregation function doesn't have to be plus. I mean, in this little paper that we wrote here, with some of them we did a mean or max. You can combine all of these things. You can also take several and then think of them as feature maps and combine them into one big analysis at the end of the day. So what I'm saying here is, this is just the starting point of graph networks, right? What we are doing is we are making our C and N here more and more abstract. We are not making a choice of the space it lives in. We're not making a choice of what defines a neighborhood, what defines closeness. None of this. We're basically giving the network now as general as possible, description of my nodes with given edges. And at the end of the day, your network will have to essentially learn what's the best combination is. Yes?
I'm still confused by the same thing that Jackie was confused by. So W, the classical one, is let's say 40 by 40 matrix.
Yeah.
A is a 5 times 5 matrix. So how do I multiply a 40 times 40 with a 5 times 5 matrix?
Oh, here. No, sorry. This object here, this also lives only in the space of. So this is this was, okay.
So it's different W's.
Yeah, I mean, these are different. This is not the same W that I had before. The other W also had other indices, right? I mean, so this is not the same. This is a W that links the individual nodes. So here, okay. In that case, it runs over all neighbors around. In the original form, we had the double index over all neighbors. Here now, I'm basically dropping one index. I'm just keeping one index for the node. I don't have the two-dimensional. And then J is really running over the nodes around. And they are defined in principle for those 5 nodes. That would be a 5 by 5 matrix. And here, I mean, this is basically the matrix gets split into a general interaction matrix. But it doesn't matter what W has. If it's not talking to the neighbors, it doesn't matter. Right. So these things only have they have these structures, diagonal structures. Yeah. I mean, sorry, a little bit of abuse of notation. But the idea is really the same. So you're running over a graph, and you're constructing a filter function, which now can be as general as you want. Here, a general filter function as a function based on the information, or which edge links two nodes, or which nodes are by no means neighbors. Yeah.
You think that just complexity? It's just what we did in the first
yes.
lecture. Instead of taking the sum, it doesn't work because it has a group structure. You just define the ReLU or the map.
Exactly. It's much simpler, right? It's a much simpler.
If represent more complex functions.
Exactly. Or more complex systems, right? I mean, what we're doing here is not particularly complicated if you think about what people do, professional machine learning people do. If I tell you I have a sparse picture with 50 plus minus somewhat entries of 2,000 pixels in the picture altogether, that's not very challenging, right? If you think about it, the professionals do that a much harder job there. Okay, so these are these graph networks. The graph networks, you can the graph networks you can play with. A bunch of things that are important. First of all, who tells me that I can only run this over neighbors? I should be able to also run this over neighbors and next to neighbors if I want. For instance, I can make that bigger. My choice. Question of the complexity. What can I afford, right? Next question is what is my aggregation function? So I can choose whatever I want. The next question is, am I pretty sure that my construction of the edge weights is stable with training, because then I can just update I can just update the W values on the edges, or do I need my network to allow for new edges to be constructed? For instance, the network could decide at some point that is not sufficient, it also wants to have that, but that really doesn't matter. Right? Then the whole thing becomes more complex. Of course, at the end of the day, you want that. you want to learn these things. Right? And there's a million different ways you can train like these graph networks. The other thing is, when you look at this aggregation function in general, you can implement all kinds of symmetries in your graph network. Right? If, for instance, if aggregation function only depends on the difference between xi and xj, well, your network's translation invariant, right? The information is always dependent on the difference. Or if it depends on the absolute value of the difference, it's rotational invariant, right? Because that's the edge information. That's the way you link two nodes to each other. So this is the point where you can play with like symmetries, representations, all of these things. This graph network here, like I was talked about, is in particle physics. The realization of this is called particle net. And that particle net, if you look into this top tagging challenge that I showed you earlier, that's the winner. That's the best one we had in 2019 when we worked on that. So the graph network, this is a graph convolution network particle net that is possibly the best and the most versatile top tagger or jet tagger today. Because you can put in all kinds of information, you can put in symmetries, you can describe your system with some kind of vector representation, crazy stuff, including charges and stuff in the point cloud. You can take any information you want, right? So it's very flexible, very, very powerful. And this is why it won. Now, yes?
So I didn't quite understand. Is the metric one of these things that the network learns, or do you include?
In principle, if you ask me, I would want it to learn the metric.
Okay, but this particular one.
Yes.
Where does it come from?
Yeah.
I didn't understand this.
Which, this one?
Yeah, the one you wrote. Yeah.
Oh, this was an analysis of this kind of point cloud representation, putting just these 4 vectors into a neural network with a free combination of 2 4 vectors, and then you see which of the, you basically learn the metric between 2 4 vectors that allows you to do top tagging. And that's the metric that comes out.
So ideally, you take your point cloud, you make it learn that, and then you feed it into the particle.
Yeah, I meant so. Okay, now, next question. You're driving me. So next question is exactly this is nice. I have these nodes, I have these edges, I have neighbors, and that simplifies my life. But the fact that I assign neighbors here throws away information, right? Because I am, by saying this is a neighbor, and this is a neighbor, and this is a neighbor, I'm also saying this is not a neighbor. Which means information from 1 to 4 and 4 to 1 is not flowing. It's not foreseen in my network, so I'm throwing away information. Now, in a regular, typical applications in imaging, that's not too bad, because if you think about an image, what you're typically looking is for local patterns. I mean, you want to know what's a car, and your car wants to know what's a tree, right? So to not hit it, and all of these objects are kind of local, right? And if you think about it, the decision of your car, your self-driving car, to avoid that, say, tree here, is unrelated to the question if there's a bird in the sky. It doesn't matter. This is actually causally disconnected, right? So it makes sense to simplify your life with these graph networks, such that you can describe more complex objects, images in that case. Yeah. Now, replace images by language. If a sentence, or a paragraph or something like that, right? Words. For words, the situation is totally different. Because if you think you are translating something or trying to understand a text, you can't, proximity doesn't really matter, right? It's not defined. I don't know. I said I don't know. A language, dependent English, you translate something between English and German, right? We know this, in German, finish this sentence and then you add all the verbs, right? And like, in English, it's like, totally different. And sometimes you have an inversion and these kind of things. So you don't know. So the assumption that I'm very willing to make for images, I'm not willing to make for language recognition. So what I would do for language recognition is I would use a graph that's fully connected. Like, every object here is like, connected to everything else. But that scales horribly because we are effectively back to like our old situation, right? I mean, now we have like a big matrix and we have to go through that. So this is not efficient. The other thing is, yeah, I mean, I'm connecting everything to everything, but there must be a smart way of doing that. And like this fully connected graph network will work, but it's not turns out not to be the most efficient way of like combining these pieces of information and like telling me what's important, what's not important. No, that brings me to the last classification network I want to talk about, and that comes from language recognition, and it's called the transformer. And it just solves that problem. Yes?
The reason we move past the CNN is because it's not good enough or because it's computationally too expensive. If it's 40 by 40, it cannot imagine it's too expensive computationally.
Well,
so you have to reduce the...
Yeah, what it turns out, like, if you look into the top 10 competition, you see the CNN was doing fine. But there's a few things that the convolution network on the images can't do. Like, if you do it on images, for instance, I wouldn't know how to include particle charge.
Independent of computational power.
Independent of the computational power, I wouldn't know, like, how to. Now what you can do is you can stack images on top of each other. Right? That's you can do. You can make, like, effectively like a vector of images. But then closeness in one of those vectors and closeness in the other, like, a vector component might be different. So, like, it's not very easy to do these things. Some people have tried this. Another problem that you have with the image representation is that you have two pieces of information from an LHC detector, colorimeter and tracking. Colorimeter is, like, limited in resolution, but it finds neutral and charged particles. Tracking has a much better resolution, but it sees only charged particles. How do you combine these pieces of information? Right? Now, if I use a point cloud, I can just put this in. Nobody, like, there is no format, right? I mean, point cloud is format free. And now it learns, the network can learn these things. Right, so you have much more flexibility. If you look into top tagging challenges, you see that the performance difference between convolution network working on images and, like, the graph convolution network is there, but it's not huge. Right? But it's still better. I think if you go for more challenging tasks, core gluon, for instance, discrimination, then at some point so it's a much more subtle question, and then the more advanced network, in that case, the graph network will win. Yeah.
So now we're still using particle flow candidates as our input. If we would go to like lower level data with your network, we go to sparse again and perform reverse.
You want to go beyond particle flow. The problem, I think, there is probably the reliability of the data. I mean, you see, like, if you particle flow is relatively well-defined and stable, like, because you're actually constructing something, like, and these things are, like, at least calibrated in some way, and, like, we know if you just put in, like, if you just take the electronic output of the colorimeter, right? I mean, you have to deal with noise, you have to deal with, like, all kinds of artifacts, so it's much harder. So you're completely right. At some point, the question is, what do I put in? High-level observables, the answer is not anymore. We used to do this, but not anymore. At this stage, I would think particle flow objects. There's a big, important question here as well, and that's pileup subtraction. I'm not going to talk about that, but, these images is not what, like, are not what you see. It's certainly not for the high luminance LHC. For the high luminance LHC, you see, like, these images, and then you overlay, like, 200 pileup events, which, like, induce a huge amount of noise. Probably a network can also subtract this, but you can basically do your standard, like, denoising, pileup subtraction, and then you get your particle flow objects, and then you work with those because they're more resilient. But, I mean, I don't think this is the end of the story. I mean, that's going to change, I think. So one step after the other.
In terms of like a figure of merit, in terms of, let's say, top tagging efficiency,
yeah.
How these things will stack against each other, or is there a number you can
I think it's in the paper. So what you see is like, the best, the best networks, like, of each architecture for a given, like, signal efficiency of whatever, 50%, 30%, or whatever you do. You like phrase this in terms of the background rejection. And I think they're closer than like a factor of 5 within each other. I think I need to check the numbers, but you can look, there's a table in the paper. The traditional taggers are much worse. I mean, a lot worse, like 10 worse than the worst network. I mean, we didn't find a single neural network that was as bad as the classic taggers, or nowhere close. So in other words, what I'm saying is using machine learning for these things is a big step forward. Like which architecture you use is something that we need to think about eventually. But there's a lot of, like, performance is only one aspect, right? Resilience is another one. Like, you want networks not only to be performant, but also to be stable. I think, like, like uncertainty estimation for these kind of things is another aspect. You want your networks to be, like, you want to be able to calibrate, like, your networks, or you want to get an uncertainty from your network. So these, like, all open questions. Computing time is clearly a question, right? I mean, in training, right? I mean, we're training these things, like, like, I don't know, like the current data set is, I think, 100 million jets or something for multi-class tagging. So, like, we have, we're training them on lots of jets, and you want this to be fast. Yes?
Precisely about that, you said we use this graph network to simplify our life, but what we do is we insert another matrix within the multiplication, so we take actually more time to do this, but we do it still because we reduce the amount of information to what is really mattering and I get better output.
Yeah, in a way, this is a smart representation. So, like, what you're doing is you're investing your time in learning the edge weights, and you're not wasting time running over, like, unimportant, like, sparse images. So, yeah, you're focusing in network. This is always the question of data representation. How do I, like, what's a smart way? It is very difficult to construct, like, data representations which, like, make your network generally more performant. I mean, without specifying what you want. Because you can help networks to, like, learn one feature better. And what turns out, like, in practice is then that it's going to have a horrible time learning another feature. So, like, there's always a balance. What you can do, though, is you can try to, like, design your network such that it learns, like, the actual structure, the symmetries, or, like, of your system easily, and doesn't waste time on stuff that is not important. And that, I think, that would be a case here. The other thing, by the way, I should say, like this here, these edges. The graphs with the edges and nodes. In principle, this is like permutation invariant. It doesn't matter how I number these things, right? I mean, the network, like, will figure it out, especially when it learns the edges, which here is not the case. Yeah. We're talking about this, the mother of, like, all matrices. So let me just write down the picture, like, how, this transformer does it. So the transformer is, if you want, the language recognition equivalent of a fully connected graph network, right? And I'm just, like, want to introduce it, like, because it's, I mean, it's just the mother of all matrix multiplications. Okay, just like, I'm just copying this, like, our picture here. So imagine you have, like, input data, and, like, for every, like, for every phase-space point or every event, or like you have a feature here, x1, no, for every, like, right, for every object, I need to get this right. Yeah, so these are C, capital C is the number of constituents. And x1 has, for instance, like, with the 3 vector, it would have 3 entries. So that's, like, one constituent. So this is constituent number 1. Number 1. Okay, and now what you want to do is, this is fully connected, you want to, like, somehow define a measure, like, how close, or, like, how, like, all these, like, different constituents here are related to, say, constituent number 1, right? So what you do is you construct yourself some kind of a matrix, like, that, like, first of all, takes this information in x1, which is a vector in itself, and like, turns this into an appropriate vector, q1. Like, for instance, you could go from x, y, z to like, pt, phi, and eta or something like that, right? And then you take all of these things here, and you construct yourself, and then we call this q. Okay, and this is called a weight matrix. And then you construct yourself another matrix, that's wk, right? That out of these x's constructs like, objects k1 to kc, and the way they're defined, like, then combined with these q's is by scalar products. So what you do is here, like, you project this onto my relevant, like, reference vector q1. You project all of these, like, q1 to kc. So you take your, like, all your you take all your, like, input 4 vectors or, like, constituents, and you, like, choose a different representation here, an appropriate representation, and then you project them all to each other. This is nothing but a basis change, right? You apply a softmax information here, so, like, you get these are scalars, right? These are basically scalar weights, so you can work with them like softmax, but, like, this just defines some projection onto your reference vector q1 for k1 and to kc. Okay, and then you define yourself another copy. So these are the key, it's called a key matrix. And then you take another copy, matrix here, where you, again, start from x1 to xz, and you change them, represent them as a new set of, like, vectors v1 to vc, and you combine those now with these a's. So then you have, like, a to a1 to v1, ac to vc. You add all of those up, or some other aggregation function, but that could be an aggregation function plus, that gives you a number z1. This number z1 tells you, in some totally abstract space, how x1 interacts with everything else by a bunch of projections. This is just linear algebra. So what you do is, you're choosing an appropriate, like, or the best possible, and you're training all of these matrices. You're choosing a representation of x1, you call that q1. You're choosing representations of all the other vectors, x1 to xc, call them k1 to kc. You project, right? So you get these, like, scalar, like, these are just new coordinates relative to q1, right? Now, you're doing another, like, matrix multiplication here, matrix transformation from x to v. You're combining these, like, coordinates here, like, with these new basis vectors, right? You add them up, take the length of that vector, that's your output. Probably, if z1 is big, there's, like, I don't know, actually, I don't know. So, like, it's a new representation. It's the mother of all matrix multiplication. That thing, yes?
This is all linear.
Yeah, this is all linear. This is all linear algebra at this stage. So, this thing is called a transformer. And, yeah, this is going to be horrible online. But, what should I say? These kind of constructions, with all the freedom you have, with all these, like, with all these matrices, all these representations, all these basis changes, like, from here and here and here and here, like, I see how they are very, very expressive. I can see how you can actually work with them, how you can extract information, how you can understand, like, sentences, how you can link, like, different like, words in a sentence or a paragraph through that. I understand all of this. The problem I have with this is that it's yet more abstract. So, like, this is currently the state of the art, if you want, I think, in abstraction of, like, fully connected graphs, or, like, fully connected point clouds, or what you want to call it in our case. And yeah, it's the first time, I think, that our field is embracing something from, like, natural language recognition, because there is another thing. The tool is called the particle transformer. that you can also like use to tag jets, which I think is even a little bit better than like the particle net, the convolutional graph network. Yeah.
How do you find all the W's? What's your loss?
Train them. That's your network. Train them. That's your network.
Yeah, with what loss? What is your label? What are you trying?
Oh, this is all classification. All the same loss function. All classification. Top versus QCD.
Your output is the Z1 is the Z. I don't understand what's your prediction. Like your input is the X.
Yeah, your Z's are the intermediate representation of your data, and then like you put this into your classification tool. Like you're producing a whole lot of Z's right here, and you're basically you're changing that. That's the representation of your data. You're piping that. Then I think that could just go through fully connected or I guess fully connected network. I don't know, and then you train the classification.
It's another network. It's a pre-processing network. The other network.
Yeah, you can call it a pre-processing network, when like but then of course it's not quite fair because like when you do this like the transformer pre-processing, the actual task, the idea is that the task becomes very simple. Or in other words, it's a pre-processing network, but that is trained together with the classification network.
Yeah, again, but still, Z is not the prediction.
No. This is that's my representation of X.
But you refuse to go to pre-processing because it does a lot of the work itself. Because
No, it is. Yeah.
It's supposed to be a very convenient representation.
It's a very efficient or like powerful. Let's call it powerful representation. Yes.
I don't understand why.
Because I don't understand why either. Sorry, YouTube world. I don't understand why. I know, and there's a reason why. Because this thing is incredibly flexible. That thing can learn anything, right? I mean, this is like such a general representation. It can learn all of these, anything you want, right? So what it is a fully connected like point cloud. If you think about it, like it really like links everything to everything. So it's clear why it's potentially powerful. It's a pain in the ass to train, probably, like for language problems. But I mean, we know language problems are super hard to train anyhow, right?
You can say that just about any neural network, that everything is connected to everything, and then you learn.
Yeah.
So why is it more complex than just a neural network? What does it add? It's not more complex than just taking your input and then having whatever number of layers in your network, and initially connecting all of them and then training.
No, that's correct. It is more complex in the sense that for like, for instance, a graph, you assume something about neighborhoods. This doesn't assume anything.
So it just goes back
This
to
learns,
what we did on Monday.
yeah,
Okay.
yeah.
What's the information in the Z's that you acquire by doing this that it was not in the X?
What it does,
The information and the correlation.
yeah, essentially you're doing a basis transformation that allows you to optimally learn correlations between the different parts of like your data set, like the different ingredients. In our case, the different constituents, and it's extremely general. And there's no shortcuts. There's no like neighborhood that you give it before. There's no metric you're trying to guess ahead of time. This is like this is all going to be trained here in this pre-processing. Yes.
I have a very specific question that I was thinking, would it be able to make positive correlated, like for example, with convolutional networks or the transformers?
You decorrelate from the jet mass, for instance.
Yeah,
Oh, well, we know that is another hard problem, right? I mean, in principle, decorrelation is, in machine learning, it's conceptually it's simple, right? You basically tell the loss function, don't take that piece of information, train without, right? But we know in practice that it's actually very hard to do. I don't know how I haven't seen, you have to ask Tilman, like, it's like, I don't know what like the performance in terms of like, the performance difference is between images and graphs and transformers when it comes to correlations. And if there's any like good tricks to do that better. There is a study on that which you can look up, and that is, what was it? It's a die-bottom resonance search where you're trying to train a tagger independent of the mass of the resonance. There's a CMS, Ruelin wrote a paper on that. I think it's a CMS study. But I can't tell you, I cannot tell you, like, I didn't play with those things in decorrelation. Yeah. Any case, I didn't want to go into this too much because, well, I'm not an expert on transformers. I'm also, I see how they work great, but like, I think, like, I don't know, they kind of, I think to me, I don't know, I don't like them. And that's bad because they're the best networks on the market. So like, that is my problem, not their problem or your problem. It's just, they are very extremely powerful, extremely flexible. Like one thing I should say that I haven't seen yet, but maybe somebody has an idea, is a good visualization how these transformers, what they do. Right? I mean, what is actually this basis change? Like, what does it do? What does it correlate with each other, and so on and so forth? This self-attention thing here. What is, yeah, how can I visualize that? I haven't seen anything like nice personally, but if somebody knows something, tell me. That might actually help me, like, come to peace with the transformers. Honestly, I like these graph networks like a whole lot better. This is all because I know what the metric is. Okay. One last thing I just want to talk very briefly about, and before we go into like, oh yeah, if we're going into like the last application of classification, I think to me the most exciting question for like this classification is how we can use or how we can incorporate symmetries into those taggers. Why is that? Because we have seen that the graph networks did extremely well, and most people think, and I agree, that the big step from like convolution networks from images to graphs is the permutation symmetry. It doesn't matter what order you put the constituents, right? If you look into this like aggregation function, there's also a CMS study that did some really nice work, now making these like this aggregation functions, respecting Lorentz symmetry. So we can, and that helps with the performance of the network. So I think symmetries are the key to better tools at the LHC. Why is that? Because, well, you know this, right? You teach theoretical physics 1 and 2, and then at some point, MI comes up, right? And symmetries, the whole role of symmetries. And then in practice, in our studies of physics, we never stop talking about symmetries. I mean, it starts with MI, and then the rest of your studies is all symmetries, right? At some point, it's going to be whatever space-time symmetries, or it's going to be non-abelian gauge groups and all kinds of stuff. But it's all we're all symmetries driven. And if you think about it, our data has a million different symmetries, right? I mean, for instance, an LHC detector is rotational invariant, around the axis, the beam axis. A jet image, once you center it, say on the central cluster, is also rotational invariant. It doesn't matter, right? It also shouldn't, for a jet, if you don't correlate it with other jet, it shouldn't matter where it is in the detector. That's translational invariance, right? The relation between, say, a jet image and the transverse momentum of your top or quark hitting the calorimeter, that's Lorentz boost, right? I know, what that does to the geometry of your image, right? So you have all of these symmetries. We have invariances, for instance, I know from quantum field theory that if I'm a quark, and relatively hard quark, and I radiate a soft gluon, it doesn't matter. Quantum field theory tells me that. It shouldn't matter. I also know that if I'm a gluon and I'm splitting into a QQ bar pair, it shouldn't matter if I analyze myself as a gluon or analyze myself as a QQ bar pair. Invariances, same thing. Based on quantum field theory, it's not going to be broken by some bloody detector. So I have all of these invariances and all of these symmetries, and so we need to work with these symmetries, I think. And there's just a language thing I want to introduce. You can start reading those papers, and that is very simple. And then we can talk about later, the details later. So there's two kinds of ways you can have a network incorporate a symmetry. The first one is called an equivariant network. And the equivariant network basically says, if I have a network that acts on an object X, an event X, and I have a symmetry operation acting here on X, right? There should be, this is a bad abuse of notation, there should be a symmetry operation that I can have act on the network that inverts this effectively. We can actually write this like equivariance condition in a slightly like more convenient manner. So, or if you have a network that gives the same output for two phase space points x1 and x2, right? And now I do a transformation S on those two x's, then I find that f theta von x1, f theta von S of x1 here is S f theta of x1, right? Parentheses, is, according to that rule here, S f theta of x2, and that is by our rule here, nothing but f theta of S of x2, which means I can take a network and I have two inputs, x1 and x2, and I transform those networks, those two inputs with the same, like some kind of symmetry transformation here, and the output for those 2 points after transforming them also stays the same. So the network respects that symmetry, right? Important, the network respects the symmetry, but this is not a network that, like, is fully symmetric. So like the next step would be an invariant network. An invariant network, and the invariant network is much simpler, is the network output of S of x is the network output of x for x, right? So we have two definitions of two ways that a network can respect a symmetry. This one here, the equivariant network. And there's enormous literature it's super interesting literature on equivariant networks. And this is the invariant network. The invariant network basically says, I take a bunch of jets, or jet space. I construct myself some kind of representation space. And the invariant network will basically say, all jets which I can be constructed out of my original jet through any kind of symmetry operation, all end up in the same spot in my representation space, right? So these things are super popular and very lots of literature. What I want for LHC is for tagging is that, right? I want a representation that basically incorporates all the symmetries and reduces the complexity by basically removing it all and say, let me go to a minimal basis where I'm just using the information modded out the symmetries. And then I get a much smaller representation space. I can work with that better. I can be more efficient. Yes?
We use this already on the trigger level or way beyond? If you put a trigger, you would speed up a lot of things. But for example, if I put in, Lorentz is a very interesting assumption. I can't search for violations of Lorentz invariance.
Yes. Oh, that is true. You should only put in the symmetries where you're very, very, very sure they exist. Because you're losing, by definition, you're losing the sensitivity, right? And if you're putting in something that, okay, shouldn't we make jokes, right? Some symmetries are broken by your detector, right? So if you try to mod out those, you're actually making it harder for your network. And you get funny artifacts. So you only put the symmetries in that you're really sure exist. And the way you want to put them in, and I can talk about this in the break if you want, this is a method called contrastive learning, where you actually take those symmetries, you define them through acting on your training data. You modify your training data, and then you say, okay, that's my symmetry structure. That's a good definition of my symmetry structure. So this is all the training data that is equivalent to my original generated data, and I learn this and put that into the network. So you don't actually put it into the architecture, you put it into the training. Yeah. I just want to say this, to me, this is a hot topic that's coming up. Not a whole lot of papers, but it's such an obvious thing for particle physicists to think about the symmetry structure. And as I said, this I think there's the Lorentz invariant tagger. I mean, actually, there's like probably like 4 or 5 or 6 Lorentz invariant jet tagger attempts. As I said, one of them was ours, but there's like, a lot of, many. We've been doing that for a while. Okay, now, tagging is nice. But you know what? Yes?
Maybe before can you say something about how you, like, say you know what the symmetry you want to cause, how do you make the network invariant, for example?
No. I cannot tell that because then I don't get to my last topic if I explain how that goes. But if you want, you would have to read it. It's in our chapter 2.4, Symmetries and Contrastive Learning. That's one way to describe by that you can use. I don't want to go into it because I have only limited time, and I want to tell you something in machine learning that's different from what people have done before and always done, and that's cooler, right? I mean, tagging is nice, but you see, I don't know, I don't really remember, when did I write my first top tagger? Actually, my collaborators and I were that's like forever ago, like 15 years, I don't know, long time ago. Tagging is not a new thing. I mean, jet tagging is like Tevatron, like super old task, right? I mean, and it was always critical. So it's totally clear why experimentalists want to do this better. And neural networks do this much better, right? Thing is only, it's extremely hard work making these better, and conceptually, it's still pretty clear what these things do. You just see that the ROC curve gets better and better and better and better. This is super important because think about it. We had that example in the break recently. You want to extract a sample of TT bar Higgs to BB bar events, right? From your data. That requires, if you want to be sure, 4 BTECs, right? Now, you're collecting, your machine is producing data, and you need a certain event sample size to do your analysis because that defines your statistical uncertainties on the measurement of the top Yukawa coupling or whatever, right? So now, imagine you can get your top tagging efficiency a factor 2 better, right? Which is a huge step, and at bottom the B tagging a factor 2 better. This is that's a huge improvement, but imagine you could, right? Then the data luminosity that you would need to get a certain sample size of TT bar Higgs 60 BB bar events, right, would be reduced by a factor 16. Can you imagine how much energy, effort, power, time that saves, right? So it is totally clear why people want to do get better taggers. It's a huge, they have huge impact. And at the start of every analysis, there's a tagger if you want, right? I mean, particle identification. So it's a key task you can't do without, but it's not cool. Sorry. So what's cool? Cool is something that we haven't tried before, and that is we have always talked about supervised classification, top versus QCD. But I don't care about top versus QCD because, for instance, because they're both standard model. Right? And I'm a theorist, I'm in there for the BSM, you heard Christoph. I don't care. I also don't care about coupling measurements all that much, right? I mean, coupling measurements are just a tool to find new physics. So what I want is, I want a tagger to find new physics. Let's do jets because I told you they're simple. So I want a tagger that tells me, well, I've seen a lot of QCD jets in my life, and that's not a QCD jet, right? So these things are called autoencoders, and they exist. And this is a generic machine learning thing that I don't think people have done a lot in LHC physics. But if you talk to the machine learning community, I mean, this is they've been doing this for a very long time. For instance, you have a business network, and you want to know if that business network has been hacked. Well, you watch the network traffic. If the network traffic becomes funny, you say, oh, this thing has been hacked. Switch it off, right? Or Facebook looking for bot posts, right? So you're looking for some account and watching an account, and they do always the same thing, whatever we always do, or very predictable, and all of a sudden things change. Well, then this account has been hacked. Shut it off, right? So this question in big data is not new. In particle physics is new. So what you can do is, it's a very simple idea really. So what you do is you take your jet images, think jet images again, And what you do is you construct a network that's called an autoencoder, which basically has a bunch of layers to construct the same jet image. So you're training a network to go from X to X prime, to map an image on itself. Now that's not very hard, and that's probably going to work, right? Now, make it harder for the network. You make it harder for the network of, like, in these layers, and these are fully connected layers, but there are no skip connections. So, like, you make these layers smaller here, right? Smaller, fewer weights, fewer degrees of freedom, and now you're asking the network to learn its own structures, right? And at some point, there's a limited number of weights in here, parameters that you can train, you can use to describe your images. And at some point, ideally, we should be able to train our networks such that these degrees of freedom that are described here, that they are well suited to describe the data that the network has seen. And the moment something kind of unexpected happens, it's not going to work. The network would need some other degree of freedom to describe it, but it doesn't have it because this is narrow. So there's no freedom, so what it does is it actually it produces a bad reconstruction error. And the reconstruction error is just for some kind of x minus x prime squared sampled over some data distribution p data. That's a reconstruction error, and this is an MSE. And that's also the simplest loss function you can have for that. So we're basically training a network to minimize this loss, which is the agreement of this image with that image, giving it lots of QCD jets, for instance. And you're sampling over the data set. And then you're making this thing that's called a bottleneck. You're making that small. And that's the idea of an autoencoder. And that's actually the thing that's going to do the job for us. Now, if you look at this autoencoder, if you're trying to understand what it does, really, let's think again. What this autoencoder does is think about the representation space I started talking about. This is going to be some kind of a representation space, right? At this stage, it's just a bunch of weights. But there's going to be some, once the network is trained to, reproduce a certain class of, say, QCD images, somewhere in here in the bottleneck, that you have a representation of QCD jets, right? And that representation is not going to suit top jets. Like, for instance, it's implicitly assuming that they are massless jets and top jets are not, so the network doesn't know what to do with the jet mass, right? The correlation is wrong. Right? All of a sudden, it needs to consider invariant masses of massive jets. That doesn't fit into the representation, so it doesn't work. Another way to think about this, though, is totally different. It's a compression tool. What it really does is, you have a lot of degrees of freedom, and then this bottleneck has very few degrees of freedom when you're writing down a representation. That's smaller, and that's a compression. And this, yes?
How do you know which size you have to make the bottleneck?
You don't. You play. You don't. You can't. I mean, yeah, you don't. It actually, in early studies we did, actually depends very much on the representation of the data. So it really depends how efficient you are, right? Also, how much performance you want. You can actually, with the size here, you can play the performance. Yes?
Could you use this instead of the graph convolution network? Is it pre-processing to the CNN? Use this to compress the data and then feed everything the bottleneck to the CNN instead of the full image?
People are thinking about this, yeah. Representation, yes. The problem at this stage here is I'm not actually giving any structure. So this is an autoencoder. It's called an autoencoder. The problem is I'm not giving this thing any structure.
Yeah, you learn the structure, the network learns the structure.
Yeah, but how do you know that it's smooth? How do you know that by some measure two images here are similar? They're actually close to each other here. You don't, right? This is you would.
You don't need to. If you trust this network, if it has a low loss function, then you know that this is a compact representation of the data.
Exactly.
You don't need to know the translation keys.
No, but you would want that. So what I'm getting at, you can actually do better. You can have loss functions that that enforce a reasonable, it's kind of a metric or distance measure here in this space, which is then called a variational autoencoder, and that does exactly that. So a variational autoencoder does exactly that. The variational autoencoder produces a representation in this space with which you can then work, and you can do stuff. Like, for instance, you can sample out of it, or stuff like that.
Representation to respect some sort of matrix that you defined on your initial thing.
Yeah. Like, if you want, like, yeah, some kind of resilient representation. Yeah. Okay, so this is a variational autoencoder. The problem with these taggers, for the LHC, is the fact that this, like, you know, representation here, this reduced representation, is super correlated with compressibility. So what happens in practice is that if you give the network a bunch of QCD jets, right, and it learns QCD jets well, a top jet has, like, you know, more features. It has more prongs, it has invariant masses, so it'll catch the top jet as not being very much QCD-like. However, if you train that thing on top jets, and you give it a QCD jet, the immediate reaction of that network will be, okay, well, that's just an extremely simple top jet, right? It's nothing. There's no feature in a QCD jet that's not in a top jet, but there's a whole lot of features in a top jet that's not in a QCD jet, and so this is asymmetric, right? So what you need to do is, can I have a few minutes extra, Gustavo? Just a very few.
Okay.
Please, please, please. Pretty please.
Only because you asked nicely.
Oh yeah. So I want to train this autoencoder, and I want to somehow, like, you know, find a way that my autoencoder is not only sensitive to features. Well, I mean, so this thing is sensitive to features not in the training data, right? Let's check. But you want it to be sensitive to features. So this is new features. Oh God, wait. Let me just write this to new features. Features, that's okay. I also want this to be sensitive to missing features. So that, like, a QCD jet with just missing features, like, you know, is also, like, you know, be labeled, flagged as a non-top jet. And that's something like that we recently found, and I'm so happy that you can do that, that I just want to briefly describe it. So here's a trick. It's a very simple trick. You take an energy-based model. An energy-based model is a very simple idea. You have some kind of an energy. You just call this an energy, right? My energy function. And the energy function here, in that case, is going to be just this MSE, exactly what you see here. Mean square error, right? And I told you that I don't like these kind of losses because this is just not a good loss, right? I like likelihood losses, for instance. But this is just MSE. This is nothing with sigma, no nothing, right? And it turns out that for these, like, you know, kind of, with this identification, I can write down an even better loss function. It's a pain in the ass loss function, but an even better loss function. And that is based on not the likelihood, but the probability. So I can write down a loss, which is the probability, the posterior probability that this thing is defined, like described by theta. And the answers I'm making is that this follows a Boltzmann distribution. Now, I can make any assumption here I want, as long as it's, like, you know, continuously dropping or or increasing, but I'm just mapping that. And then I'm turning this into a probability loss by just putting a normalization factor here. That normalization factor depends on the network training here, right? Because it's defined as, theta is defined as an integral over x, right? Whole thing has to be a probability dx e to the minus e theta of x. In a way, you can think of this Similar, like, you know, as a similar thing as like a likelihood ratio. We started with likelihood ratios, right? Except this is not a likelihood ratio. This is like, you know, a probability with a normalization factor. What's the difference between a likelihood ratio and a probability here? The likelihood ratio divides by some reference value which is typically independent of the network details, right? It's like, you know, the reference point. Here, in the denominator, I have something non-trivial, something I have to compute. All right? Okay, and now I calculate my loss function. And like this is my loss function. It's just a negative, that's like, you know, NAE, normalizing autoencoder, it's called. It's nothing but the expectation value of the log, not of the likelihood, but of this probability p theta of x sampled over the data. And I can just use that. I can use that term. It's like, you know, minus, and then the first term I have is it's this expectation value of E, which is the MSE. That's our regular loss that you find over there, right? But then you have a second term, which is plus log Z theta, P data, sampled, right? And now I can ask, like, you know, why is that interesting? What does that buy me? Well, you'll see this immediately what that buys you when you calculate the gradient of that, which is what you do all the time when you train the network. So let's do the gradient of this here. The gradient of that is the gradient of log p, and I just insert this same function. I insert the same function, which is minus gradient in theta space, right, of log p, theta of x, equals, well, the first one is nothing special. It's just the gradient of the energy or the gradient theta of the MSE, right? Okay, that's my standard training. That's my standard machine learning, like autoencoder training, plus gradient theta log z. Okay, now I can insert this z here, which is gradient plus, okay, the gradient of log z is 1 over z times the gradient of z, right? The gradient of z, like, you know, is a gradient in theta space, and this is an integral in x space, so I can pull this through. So it's like, you know, x dx gradient theta, well, e to the minus e theta of x. Getting this right? Okay, now I can do this by wiping times gradient the e here, e of x, with the minus. That's exponential, just through doing the gradient. And now I can check what I have. This is 1 over z dEx, all that. So, like, you know, I can pull this 1 over z inside. When I teach undergrads, they hate that when I do this wiping thing, but it's super efficient on the blackboard. And now you notice that this part here is just the same as here. So this is the standard term minus x, oh no, yeah, so this is dx, and this is p theta of x gradient e. And then I can rewrite in our own language. So this is here gradient theta e theta of x minus, and that is nothing but this gradient here sampled following p theta, right? By definition, if you want. So this is a sampling step, gradient theta e theta of x, like that, sampled from p theta. This is my model. Yeah. Okay, now remember that, like, you know, evaluate that gradient always on samples in data, on the data sample. So what you really want is you want here a sampling over p data, right? Well, it's fine. Like, you get here this p data. This is, again, our standard MSE loss. That thing here, though, doesn't depend on p data. So my sampling of this over p data, this is already sampled over p theta, and the sampling over p data just becomes the normalization term, and you can forget about it, right? So what we have here is, with these networks, you have a gradient of the loss, right? Where this additional funny normalization term here induces a second contribution to that gradient of the loss. That gradient of the loss has a standard term that you always evaluate, and then it has the second term which samples over the model space. And it has and it has the wrong sign, right? Now you can actually build your model, and then you can check that when you train this network, well, this first term here will just try to accommodate all the features which are in the data here, right? And then this second term is going to look at all the model features, and if they are not what they should be, it'll ruin your training. It works the other way around, right? So this is just the same MSE, but it is looking at all the features which are in the model, not in the data. And because they have a different sign, right? If this thing, the first term, wants all the features, that are in the data to be in the representation, this term here, this additional loss, defines it's essentially like a background metric. I think of this as a background metric where, all the features which are in the data, in the model and not in the data, work against you. So push you back up. So this is a really cool network, I think. I mean, it's super hard to train these energy-based models, and it's that's known. But what it does is, and that's along the lines of my story of the first and also the second lecture, is if you move away from this very, very simple MSE loss and you do something a little bit more substantial, well-motivated, useful, interesting here, and you write down a beta loss. Now this is, as I said, it's not a likelihood ratio, but it's kind of close. It's actually more complicated than that because it's a probability loss, it's a posterior probability loss. So this is kind of base theorem already folded in, if you think about it, right? Then you have to calculate this theta, this z of theta at the end of the day, but your gradient of your loss function gets something like a background metric. And the background metric works against your regular optimization. So what this thing actually wants is it wants to accommodate all the features that you have in the training data and no others. Other features goes up here, right? So that's a nice thing we recently discovered. It's called a normalizing autoencoder, and it's technically we can talk about it. You need advanced Markov chain stuff and a lot of numerical tricks to make that work because it's nice to write it like this. But at the end of the day, there's a point in your life you have to calculate z theta and the gradient of it, right? And that's hard. And I don't want to go into this, how you do this. It's fairly technical. But what you see is that it is actually possible through a smart choice of loss function to do with these autoencoders what we want to do, namely not only incorporate all features of the training data in the model, but also make sure that features which are in your test data are not in the model to count against you in the MSE. Remember, the energy is nothing but the MSE. It's just the background of the MSE. Yeah? And the other reason why I like this kind of model is because now I have an autoencoder that works, that does what I want to do, and it's not even more complicated. It's not a more complicated architecture. It's it's the same. I haven't talked at all about the architecture, right? This is the old autoencoder. You can use any simple network you want. This is just a smart choice of training. And of course, that's nice because you can take your regular network and you can just make it better by asking a better question. And yeah. You can look at some nice plots in the lecture notes at some point in figure 33 or then figure 34. Let me just draw those and then I'm done. I'm not even going over time, okay? So what comes out of this is again, top tanking versus QCD. top versus QCD, because this is our favorite little example. Okay. First of all, you do top tagging. Top tagging. So your signal, well, your background is QCD, and the assumed signal that you test this autoencoder with is the tops. Then you can do the MSE here, plot like, you know, your jets here, like, you know, this is just count rate of the jets as the MSE distribution of your jets in your top and QCD sample. So what happens is that QCD leads to relatively small MSEs. That's what it should do, right? So there's a small MSE, QCD trained on exactly what it should do. Tops look like this. You cut on your MSE, you normally score, you say, okay, that's not QCD, right? I told you that this usually doesn't work the other way around, and I didn't plot here and plot anything here. For that one, I'm happy to plot it, because now you can do QCD tagging. And this is, again, the MSE. Same network, just trained on tops, and then like assuming QCD. So the simpler jets are my signal, just number of jet distributions here. Well, you're training QCD tagging, you're training on tops, and like, you know, the top distribution looks like this. It actually has a bit of a tail here, like, you know, that has to do with the way the features are distributed. So that's now tops. That's our assumed background. And then QCD. QCD actually looks like this, like that. And then it has this nice little feature that I told you about earlier. Like, you know, yes, it's looking for like features which which should be there in tops, but are not there in QCD. But, you know, there are, in this case here, some of those, like, you know, this is QCD. Some QCD jets in the tails of all kinds of distributions might have a large jet mass, so they actually do look like tops. So that you can't avoid. That just happens. And we can play with the preprocessing to make that smaller and so on and so forth. But this is the first anomaly search tool that I have seen, at least for the LHC, where you actually have a symmetric separation of tops and QCD. And the last thing I want to say, of course, you're not interested in taking QCD on tops. I told you that, right? But now imagine you're looking at, we had this in the other lectures. Imagine you're looking at jets where dark matter gets produced as part of the jet fragmentation and, like, you know, splittings, right? Like they're like called semi-visible jets or something like that, right? And, like, you know, that might happen. And there's two ways this can happen. The first is, well, dark matter is relatively massive, and it leads to splittings. So, like, you know, kind of like a top jet, right? In that case, you're going to look like, you know, for top tagging, essentially. You're looking for more complex objects, tell them apart from QCD. That might be true for dark matter. However, another scenario where dark matter appears in jets is, well, where, I mean, you have all of these splittings, and a bunch of them are dark matter, and they just vanish. So they're gone. So in that sense, a dark jet could also be just like QCD, no mass splittings, just fewer constituents, a little bit less complex, even simpler than a QCD jet, right? In which case, your tagger would have to be able to do QCD tagging. So like in, like, you know, real BSM life, this is important, right? Because I don't know to which end of QCD my BSM signal sits, right? So it could be more complex, top-like, less complex, just dark matter, like, you know, vanishing, like, you know, in your jet. And these kind of anomaly searches will do that. And this is why I like them. Okay, that's all about, like, classification. Tomorrow is generative networks. Questions? Yeah.
So, which takes uncertainties into account. So,
yeah.
Does it make it too complicated, or is it something which is?
I think, like, as long as it is a monotonously dropping, like, functional, like, related to the MSE. Well, okay, if you believe the MSE has something to do with like anomaly tagging, which you probably, like, you know, it doesn't make much sense to basically say, like, has nothing to do with MSE, right? I mean, MSE might not be the most efficient tool, by the way, the anomaly score. But if you assume it has something to do with the MSE, so you basically want to match this like, MSE, like somehow. No, I mean, you can take whatever like floats your boat, right? I mean, you can take like, any kind of function. You see what it does here. You see the MSE doesn't actually appear. So you can replace E by any function of the MSE that you want. The important thing is not what the form of this energy is. The important thing that the normalization factor. And actually, the other important thing is the Boltzmann distribution, because like this entire simple derivation rests on the Boltzmann distribution, which, by the way, that like in the literature is all Gibbs, but yeah. So I think you can use anything you want. You see, as long as it has a sensitivity to the MSE down here. But what's important is you have the normalization factor, and to get exactly that form here with this like negative energy and positive energy solutions, you want a Boltzmann distribution. There's also, by the way, there's lots of like in the literature, like there's lots of discussion like why that is the perfect representation, because like it maximizes the entropy and so on and so forth. Well, yeah, yeah. It also works very well.
Yes, just a second. So when you do the integral and define the precision function, you integrate over all possible mathematical values of it, not just the data set. So you take
here, that one. At the end of that, you do it numerically, so you do it on the data set, on the set.
So then I don't understand at all your point here. The point was that you also learn features that are not in the data, because the second term. The second term only learn stuff that are not in the data if you include stuff that are not.
No, this thing here is trained on your model, so your model can like come up with stuff. Right? The model comes up with things here. This is the model. This is not like
this is doing the learning, right? This is a gradient descent step, right?
Yes, but it.
The loss function. This is every gradient descent step uses this.
Yes. And it has two different, yes, that's a training, it's a gradient descent, it's like usual thing, but you see there is two different, so this one here is optimized on the data. This term doesn't see the data. It sees only the model. So that thing comes up with all kind of like, things that the model might have. That term doesn't actually, there's no like, this X here is sampled according to the data in the training. It's sampled according to the model here in the training. That here is following the data. Yeah. So, but like it is really different. Yeah. So this is why I'm saying it's a background metric. I think of this as a background metric because it's like it's a background metric that has nothing to do with the data sample, like the way you do it right now. But it's a background in relation to which you actually do your regular learning. This is not sampling of our data. This is calculating stuff on the model that you have at a given time. Yeah. I have to admit it's not trivial. Like, it's like thinking about it, these two ways of describing it. Like one, you think of this as a normalization here, right? And they're like, which also means like, things like, that like are not there in your phase space. Like, think of the normalization. You're integrating your MSE over, essentially your MSE over in the entire model space, right? You can think of it that way. It's like the denominator basically probes part of your phase space where like, the data has no features that it can tell you about. Like, it's like, in the remaining part of phase space where like, your data doesn't actually give you that information, feature space. So it really extends beyond. It's magic. Yeah, I think this is very similar to the question we had before. Like, you know, does energy have to be the MSE? Yeah. And no, it doesn't. I mean, it should be a function of the MSE, right? But like, you know, it doesn't have to be exactly the MSE. It's just, you know, we know the autoencoders, like, you know, the first thing you try with a classic autoencoder is the MSE. And like, you know, so the energy-based model is if you think about it, the entire like everything that I derived here, from here and then down here, right? The fact that this is the energy is the MSE never features, right? I mean, like at the end of the day, the only thing I said, like, you know, once we were here, I said, well, this is the original standard autoencoder training when the energy is the MSE. If you have a way where, like, you know, you can train your autoencoder on a modified version of the MSE in some way, right? You can insert that. Nothing stops you from doing that. I was the same question. Like, you know, doesn't have to be. The energy doesn't have to be the MSE. But you need that representation.
Like the autoencoder is exactly what you were saying about bottleneck, right? That is like...
Yeah. The autoencoder, the standard bottleneck, everything, I think it's said here before, like it had the loss function was the MSE. This is exactly corresponding to this gradient of the MSE. Yeah. It's nothing different. Yeah.
Okay. Now we understand.
Everybody dead. So.